we will discuss for about 20 minutes and then we will proceed with our quiz. I will try to keep it within 20 minutes as well. So this is an extremely useful bound. It's similar to the Markov inequality and Chebyshev inequality. It gives an inequality or a bound on the probability, tail probability. For example, if we have a density function like this one, so take some value A, you are interested in finding the probability that x exceeds A. We normally call it as the tail probability. So that is a rare event that it exceeds some value. Such probability measure, if you want to find, then Chernow's bound can be used in those contexts. The most important thing is this bound uses moment generating function of x. Using the moment generating function, it gives the bound. So in order to look into this bound, first what we do is we look at certain ingredients that we would require in order to arrive at this bound. First thing is that we will look at this step function u of x minus e. So that is defined as 0 for x less than a and 1 for x greater than or equal to. It has a step at the point. So if you draw it, if this is a, then it is right. So this is the unit step function. You will also look at one more function, which is e power of t into x minus. You will also plot it in the same place. So if you look at this function, when x equal to a, when x is a, then this is 1, e power of 0, 1. So this function will go through this point, and it is an increasing function. Okay. So it means that for x less than a, it is negative. So it will be like this. And then when x exceeds a, then it is increasing. It will be of this. This would be, this is u of x minus a, is t of t into x minus a. These two. So what you can easily note is u of t, u of x minus a is always less than or equal to e power of t of t into x minus. Okay. This is bounded by this. We will make use of this known result in order to arrive at the Chernow's. Well, now let us consider probability that x is greater than or equal to a. So what is this one? Okay, I will give example for you. That is a to infinity, fx of x is what this is. That I will write it as, maybe we will rotate this one. Probability x greater than x, a into infinity. So that I will split it into two. If integral minus infinity to a 0 into fx of x plus a to infinity 1 into fx of x. So which means that this doesn't contribute anything. It is actually a to only this one, we have just added this function. So what is this one? That is, you are up to a you are multiplying 0, and from a onwards you are multiplying 1. It means that you are effectively multiplying u of x minus a into fx of x, because u of x minus a is 0 for x less than a, for x less than a it is 0, for x greater than a it is 1. So this is nothing but u of x minus a, because up to a it doesn't contribute anything, after that it is just 1, and that is what that was. Why are we doing this? Because now we are going to invoke this inequality. We know that this is less than or equal to this. So if I replace in place of this e power of minus e power of t into x minus e, then this will be larger than that. So we get this one. Probability x greater than or equal to a is, then we will split it. We will take minus 80 outside. And then we will have e power of t into x into fx of x. And what is this one? Huh? This is the NGF. So we get a very generic, less than, this would be less than. We are getting a very generic bound for a random variable in terms of the tail probability of a random variable in terms of its MGF. Nowhere we have mentioned had any assumption about whether the random variable is discrete or continuous, non-negative, nothing. Very generic. And that is in terms of the MGF. As such, it is not very immediately useful for finding any of this bound, because this is another function that you are giving. If I am giving some value of, if I know the characteristic, if I give some a, if I can put and get some numbers, it makes sense, but that is not happening immediately. So, in terms of a MGF. But now, for then what we have to do is, this is true for whatever may be the t that you are taking. Okay, so that is whatever a you take, this holds true. So it will happen that this is also a function of t, this is also a function of t. It will take the minimum value at certain t. Even at that point, this inequality should hold. So that is when we will get we will know a tighter bound for probability x greater than or equal to t. This is true for all t. I will look for a t where this gets minimized. Even then it will be less, and that value will give me a tight bound for this. I want to find this one, which is the smallest possible value. If I can tell that this is definitely less than 0.1 or less than 0.03, it is better. The lesser it is, better it is. Okay? I cannot simply say that this is less than 1 doesn't give me any information. Less than 0.5 also is not. Less than, if I can less than 0.1 means it is much more better than 0.5. It's still better than 1 and so on. So that is what we mean by tighter. So if you do, what you will do is first you will take a normal random variable, that is x, which is n of mu comma 6 sigma square. Okay. And what is the NGF of the normal distribution mu comma sigma? We have already derived it. It is e power of mu t plus sigma square t squared by 2. Okay, it will be a refresher for your this. So this is what NGF of the normal one is. So for this, what does this Chernov's bound gives? Property that x greater than or equal to a is less than or equal to e power of minus at sin x of t, and this is e power of mu t into e power of sigma squared t squared by 2. I am putting everything here. Okay. So this is now what we will do is we will look for a t that minimizes this, and for that we will get a bound which will be the tightest bound that we can find out using the Chernov's inequality. So under what condition this will get minimized? When this gets maximized. But of course this is minus, this is plus, but whatever it is, when it's this differential of this is 0. Okay. So we will look for that. This is a minus mu. Okay. With the transport you can do. This one is 2 sigma square t squared by 2 t equal to 0. So what we get is t is equal to a minus mu by sigma square. So now the what this is when this gets minimized, and what will be the minimum value? Substitute that in this case. Sigma squared by 2 into t squared. This goes away. So this is one half of this. This is negative, this is positive. So what you would get is so this is what we get for the case of normal distribution. Okay? This is for Gaussian. So to check what it means, we will take that x is normal. We will give some value 5, 4. It means that mean is 5. Variance is 4, sigma is 2. Okay, for which we will find probably that, see, Gaussian means around 5 is peak, and I am looking for some sigma which is 2. This is the standard deviation. 2 this side, 2 sigma, 3 sigma, all will be like this. You know, this is how a Gaussian one is. We will just look at probability that x is greater than 2 sigma, that will be 9. X is greater than or equal to 9. We know that this is what we are looking for. So it will be less than or equal to e power of minus of what is a, that is the bound we are looking for. This is 9 minus mu 5, the whole square divided by 2 into 4 minus, so this is 16 by 8 e power of minus 2. So probability x is greater than or equal to 9 is less than or equal to e power of 9. That is what the Chernow's bound gives for the Gaussian space. Meanwhile, this can be arranged, and then projection, all these things can be done. Yeah, I will take 3 minutes. Then we will look at Poisson random variable. X is Poisson with a parameter lambda. Okay, so what does again we will use the Chernow's bound. So first of all, what we need is the characteristic equation for the Poisson random. How does it look like? Lambda is the parameter. It is e power of lambda into e power of t minus 1 is the MGF of the Poisson random variable. So what is our Chernow's bound? That is the Chernow's bound. So apply it for Poisson. E power of lambda, e power of t into e power of minus lambda. Okay. So this is what we have to. So e power of minus at minus lambda plus lambda e power is what we have to. This is what we are interested in minimizing it. You can everything we can do it. Please don't wait. This is what we have to do it. So differentiate and then set equal to 0. So this is minus a, this goes away, plus lambda e power of t equal to 0. So e power of t is equal to a by lambda, t is equal to ln of a by lambda. What we get. So we will substitute it. So this is at t is equal to ln of a by lambda, the exponent gets minimized, and that is when you will get the smallest value for this, and that is when you will get the tighter bound for this. So e power of minus a into ln of a by lambda into e power of minus lambda into e power of lambda into see, I am substituting this lambda into e power of t, e power of ln of a by lambda. So this one is this is gone. It will be a by lambda, it will be e power of e. This is what you will get. So let's take an example. Let's say a Poisson. Let's say Poisson with parameter, let us say 5. Okay. That is, you look at consider the number of events that occur in some interval also. That is Poisson random variable with an average of 5 events occurring in that interval. Now you are asking what is the probability that more than 9 events occur. See, this is a discrete random variable. See, we have shown all these things for continuous, but it is also valid for discrete random variable. Okay. So that is less than or equal to. So we have to put here what happens. Lambda is equal to 5, a is equal to 9. So e power of minus 9 ln 9 by 5 into e power of minus of 5 e power of 9. So this is e power of minus 4, minus plus 4, plus 4. This is what you will get. So that of course you can compute it and then find out what it is. So that is all about the Chernow's mode. Okay. We took 2 examples and we looked at it.